Your car's brakes feel different when your fuel tank is full versus nearly empty, and there's solid physics behind this phenomenon. It combines basic principles with tire behavior and weight distribution that most drivers never consider. When you fill up your gas tank, you're adding between 60 to 200 pounds to your vehicle, depending on tank size. A typical 15-gallon tank adds about 90 pounds when filled with gasoline, which weighs roughly 6 pounds per gallon. That might not sound like much compared to your car's total weight, but this extra mass creates a cascade of effects that can subtly change how your vehicle stops. The theoretical answer to whether weight affects braking is surprisingly counterintuitive. According to pure physics, a heavier car should stop in exactly the same distance as a lighter one on the same road surface. When you add weight to a vehicle, you increase its momentum, which means more energy needs to be dissipated to bring it to a stop. But you also increase the downward force pressing the tires against the road, which should proportionally increase the available grip. In theory, these two effects perfectly cancel each other out. This follows the same principle as why a bowling ball and a feather fall at the same rate in a vacuum. More mass means more gravitational force, but it also means more resistance to acceleration. The mathematics work out perfectly on paper. But real-world driving isn't a physics textbook, and tires aren't perfect friction generators. This is where the science gets interesting and explains why your brakes might feel different with a full tank. The key lies in something called tire load sensitivity. Real tires don't behave like the idealized friction surfaces we learn about in physics class. When you increase the vertical load on a tire, you do get more grip, but not proportionally more. The coefficient of friction actually decreases as the load increases. Think of it like pressing harder on a piece of sandpaper. You get more total grip, but less efficiently. Slovak researchers tested this phenomenon in 2019 using a Peugeot Boxer van. They accelerated to 75 miles per hour and then braked to a complete stop, measuring the stopping distance. Then they repeated the test with dummy weights in 550-pound increments, up to 2,200 pounds of additional cargo. The results confirmed that heavier loads consistently increase stopping distances, though the effect was relatively small under normal conditions. This load sensitivity effect becomes more pronounced during hard braking because of weight transfer. When you slam on the brakes, physics forces weight toward the front of the vehicle. You've probably felt this as the nosedive sensation where the front of your car dips down during heavy braking. This weight transfer loads up the front tires while unloading the rear tires. During a typical emergency stop generating about 0.9 g of deceleration, approximately 30% of the vehicle's weight transfers from the rear to the front wheels. This means your front tires suddenly have to handle 60% more load than normal, while your rear tires have 60% less. Because of tire load sensitivity, this redistribution actually reduces the total available grip by about 6% compared to if the weight were evenly distributed. Now here's where your full fuel tank comes into play. In most vehicles, the fuel tank sits toward the rear, often behind the rear axle or under the trunk area. This placement isn't accidental. Engineers designed it to balance the heavy engine up front and keep the fuel away from the passenger compartment for safety reasons. When your tank is full, you're adding that extra 90 to 200 pounds primarily over the rear wheels. This changes your car's weight distribution and center of gravity. The research from Slovakia found something fascinating, where you place weight matters more than how much weight you add. In their tests, 2,200 pounds of cargo placed over the rear axle actually improved braking performance compared to lighter loads positioned toward the front of the vehicle. This happens because the rear-mounted weight helps counteract the natural weight transfer that occurs during braking. Instead of having all the weight rush to the front tires, the additional rear weight keeps more load on the back wheels, maintaining their ability to contribute to stopping power. In essence, a full fuel tank can actually help your rear brakes do their job more effectively. But there's another factor that complicates this picture: brake fade. Your braking system converts the kinetic energy of motion into heat energy through friction. More mass means more kinetic energy that needs to be converted, which generates more heat in your brake components. While modern passenger cars rarely experience significant brake fade during normal driving, the extra thermal stress from repeatedly stopping a heavier vehicle can gradually reduce braking efficiency. The effect becomes more noticeable in extreme conditions. Commercial truckers have long debated whether empty or loaded trucks stop better, and the physics supports both sides depending on the circumstances. An empty truck has less momentum to overcome, but it also has less weight pressing its tires against the road. A loaded truck has maximum tire grip, but also maximum momentum and heat generation. In practice, modern anti-lock braking systems and electronic stability control help manage these competing factors. For passenger vehicles, modern safety systems largely mask these effects during normal driving. Your car's ABS prevents wheel lockup, electronic brake force distribution optimizes the pressure between front and rear wheels, and brake assist systems help you apply maximum force during emergencies. These technologies are calibrated to work across the full range of vehicle loading, from an empty tank with a solo driver to a full tank with passengers and cargo. The EPA has quantified the fuel economy impact of extra weight. Every 100 pounds reduces efficiency by about 1 to 2%. But the braking impact is more subtle and situational. Most drivers won't notice any difference in their daily commuting. The effects become apparent primarily during emergency stops, high-speed braking, or repeated heavy braking that generates significant heat. Professional race car drivers obsess over these details because in competitive driving, every advantage matters. They know that removing unnecessary weight isn't just about acceleration, it affects brake performance, tire wear, and heat management. Some racing teams even time their pit stops to minimize fuel weight during crucial portions of a race. For everyday drivers, the practical implications are modest but worth understanding. A full tank might add an extra foot or two to your stopping distance in an emergency situation. That's not dramatic, but in a true emergency where you're trying to avoid a collision, every foot counts. The lesson isn't that you should drive around with an empty tank. The safety and convenience benefits of having fuel far outweigh these minor performance impacts. Instead, it's a reminder that vehicle dynamics involve countless subtle interactions between weight, physics, and engineering compromises. Understanding these principles can make you a more informed driver. When your car feels slightly different with a full tank versus empty, you're not imagining it. You're experiencing the complex interplay of momentum, tire physics, weight transfer, and thermal dynamics that engineers spend their careers trying to optimize. The next time you fill up your tank, remember that you're not just adding fuel, you're changing your vehicle's center of gravity, weight distribution, and stopping characteristics in measurable ways. It's another example of how the physics we learn in school play out in unexpected ways in our daily lives, even when we're just trying to get from point A to point B safely. So the next time you hear someone say, "It's just a tank of gas," you'll know it's a little more than that. Every gallon you add subtly shifts mass, alters balance, and changes how your vehicle responds in critical moments. Not enough to transform your car, but enough to matter when physics is pushed to its limits. Modern vehicles are engineered with remarkable precision, but they still obey the same fundamental laws of motion that govern everything around us. Weight influences momentum. Momentum affects stopping distance. Heat alters friction. And small differences can compound when timing is tight. Driving may feel routine, but beneath that routine lies a constant negotiation between force, mass, and motion. Understanding those invisible forces doesn't just satisfy curiosity, it builds awareness. And awareness is one of the most valuable safety tools any driver can have. Because on the road, physics is always at work, whether we notice it or not. And sometimes, even a single extra foot can make all the difference. Make sure you subscribe.